this block. Okay, so last time I tried to introduce you with the course, and I tried to convince you that this first part of the course is useful for acquiring the knowledge of the basic mathematical instrument that will help us in describing a set of methods which are quite useful and very useful for PDE and financial programs. So the first set the first topic is the so-called linear algebra. And I uploaded these slides a few hours ago in the platform, this MyLewis platform. So you will find this set of slides. Of course, this is only a review of some important topic. Mainly, it's a review of the main notations and operations that we can typically recognize in using matrices and vectors. And well, I hope that you already know all this kind of techniques of this kind of notation and definitions, but anyway, we try to introduce you with this notation and with the concepts which are used typically in this field. The main object that we'll see in this set within this topic is the solution of the characterization of solution of a system of linear equations. So a linear system, which is a very important and basic step in every branch of applied mathematics. And we'll see mainly a result and a way for characterizing the solution of any possible linear system. Then we'll see some applications in the future, some applications to some financial problems. The first one is the definition of eigenvalues and eigenvectors, which is very important, which will introduce us to a technique which is called the principal component analysis, and we'll see a very successful application of quantitative techniques, of this particular quantitative technique, which is called the principal component analysis, PCA, to the field of in the framework of interest rate fixed income market. So we'll analyze a very important and special market, which is the market of fixed income, so bonds, zero bonds, swaps, interest rate swaps, and so on. Then we'll see how this technique will help us in understanding the dynamics of this particular field, which is one of the most important set of financial instruments which is currently used in the world market. This is for convincing you that this big boring part of the course is still useful for the future applications. Okay. So what are matrices and vectors? So the mathematical definition we have already seen this mathematical definition. A matrix is an array, a two-dimensional array, which is filled up with real numbers. In general, a matrix can be formed by complex numbers, but we will not treat this kind of numbers in the future. Be careful, since many computational programs accept complex numbers as normal, as usual. So sometimes you can do some operation which with real numbers are forbidden, but in practice you can do this. For example, if you compute the square root of -1, you think to get an error, but this is not the case sometimes. Okay? Since the square root of -1 is a complex number, and many computational framework can accept a complex number, so you don't get an error. And this is quite well. It's not good since you think that your code it's running well, but this is not true. Okay, but anyway, these are some computational ideas. So this is a matrix. So the important things that you have to remember is the definition. So the formal definition of a matrix will be given in this way. A, typically the matrices are written in uppercase letters, belongs to the set of real numbers with the exponent which tells us the number of rows and the number of columns of the table, of the array. Okay? So that the definition that you see here means this object in which, so an array in which there are m rows and n columns. The elements of the matrix are denoted with a lowercase letter and two indexes. The first index is the index of row, and the second index is the column. So the two indexes identify the position of that element inside the matrix. Okay? That's very easy. Consider that this is the mathematical definition, but the same problem, the same structure, you will find the same structure in any computational language. So in Python, you can identify an array with these two indexes, the number of rows and the number of columns. Okay? The position in the array. Okay, so special cases when one of the dimension, I call them n the dimension of the matrix. So this is a matrix of dimension n times n. Okay, and rows and columns. If one of the two dimensions is 1, then we it's a matrix, but with a special name. Okay, we will call it a vector. So you can have two kinds of vectors, vectors with m rows and 1 column, or vectors with 1 row and n columns. So row vector or column vector. Okay? This is important since many operations are possible within this world of matrices and vector only when the dimensions are properly given. And this is particularly true when you apply these operations in practice. So you define a matrix in Python when you want to add or multiply or do you want to do some operations with matrices, you have to look at the proper dimension of the object that you are working with. Okay. Okay. So well, this is a very short example. This is our first motivating example. When you have a linear system, then you can identify within this linear system 3 objects in the which are matrices and vectors, and then we'll see how to define an operation in such a way to compactly describe this kind of object in a very compact way. Okay, so the first thing that we have to introduce, that we want to introduce, are so you have an object, okay, which is different from a real number. So if you have real numbers, you are able to do some operations with the real numbers, some algebraic operation. Okay, which kind of operation you know? The sum, the product, the difference, the product, and the division. We want to do the same thing for matrices. Okay? Quite easy. But not straightforward. That's it. Okay? So, sum and subtraction and difference are the easiest operation that we can extend to the set of matrices. Okay? So the idea is very simple. The sum of two matrices is well defined when the two matrices have the same dimension. Okay? So same dimension, 3 by 2 plus 3 by 2. Okay? 3 by 5 plus 3 by 5. So the two matrices must have the same dimension. When they have the same dimension, you can define the sum. How you define the sum? Element by element. Okay? So the element in position 1, 1 is summed with the element in position 1, 1 of the second matrix. The element in position 1, 2 is summed with the element in position 1, 2 of the second matrix. Okay? Just look at the example. These are the two matrices, dimension 2 by 2, and then we sum element by element. So the element in position 1, 1, 3 of the first matrix is summed with the element in position 1, 1 of the second matrix. So 3 plus 1 is 4. Elements 1, 1 of the sum matrix. Okay? And so on and so forth. Okay? So subtraction is essentially the same. Okay? So sum and subtractions are so-called element-wise operations. Okay? Element-wise, element by element. And this is what the plus operator do in Python. Plus is an element-wise operation. Okay? Other kind of operation that we can define, which is slightly more general than the multiplication, the product, is the product by a number. Okay? In the matrix theory, when we use matrices as the main object, as the main mathematical object, the simple real numbers are called scalars. Okay? So a real number in a world of matrices is called a scalar. Okay? Look at this example. This is the matrix 2 by 2. The number in front of the matrix is here is an integer number. Is called a scalar. Okay? The scalar is a real number. Then the multiplication of a matrix by a scalar is simply defined as the multiplication of the element of the matrix by the same scalar. All the elements of the matrix are multiplied by the same scalar. Okay? Like this. Okay? So this is multiplication by a scalar. So the next step is to verify, but believe me that these are true, these equalities, all the properties of the sum operation, the sum operator. So since the sum operation is element-wise, and the scalar is element-wise, element by element, then we can use all the properties of the sum and the simple product. So it's distributive, it's commutative, there is a neutral element, so a matrix that when summed to a given A gives back the same matrix A. I'm thinking about 0. What is the effect of summing 0 to a given number? Nothing. So 0 is the so-called neutral number for the summation. Okay? And this is true even for matrices. So you can define a matrix made up by zeros. So fill it up with all the elements of the matrix are 0. Then when you sum this matrix to another matrix, you get the original matrix. Okay? Neutral. It's called neutral. No. Don't worry about the name. There are some commands, as we'll see, as you will see, in Python, but even in other languages, which command with which you can define matrices of zeros, for example, the zero matrix. This can be important in some application, to start with the zero matrix. Anyway, you can distribute the sum this way, you can commute the summation, even distribute the sum with the multiplication by a scalar. So nothing special. These are quite intuitive, okay, operation. Here we have the first complication, okay? The first complication is that the multiplication, we can define two kinds of multiplications for matrices, okay? In general, the matrix multiplication, so multiplication by for matrices, when you do calculation pen and papers, is the row by column multiplication. It's defined in this way. Now I explain you in a moment. Okay? This is the so-called matrix row by column product, or row by column multiplication. Okay? This is different from the usual multiplication. It's another way of doing multiplication. It's another operation. We call it multiplication, but it's really a bit more complex. Okay? How is defined? So, the first thing is that you may apply this matrix multiplication when the matrices satisfy, when the two matrices satisfy some conditions. So, the first condition is that the number, so you define the product A times B. I want to stress that in this, for this kind of operation, it's important the position of the matrices. So A is the matrix on the left times multiplication the matrix B, which is on the right. Okay? The order is important. So the first matrix A must have a number of columns, look at the example, a number of columns which is equal to the number of rows of the matrix on the right. Okay? In symbols, the second index for A, so A is a matrix n times n, must be equal to the first index of the matrix B, n times B. Okay? This means that the number of columns of the matrix A must be equal to the number of rows of the matrix B. Okay? When this is satisfied, you can define the matrix multiplication, the row by column product, okay? Which is defined by this formula. It looks a bit tricky, but look at this example. So the idea is to say, okay, I take the first row of the matrix A and I multiply element by element with the first column of the matrix B. Okay, so 3 times 1. Then I multiply minus 1 times 0. Then I multiply 0 times 1. Okay? Then I sum this product. So it's a sum of products. Okay? It's more difficult to say than to compute. Okay? And this gives us row 1 times column 1. This way, element by element and then sum, is the first element of the product matrix. Then I take first row, second column, in this way, element by element, 3 times 2, minus 1 by 1, times 1, 0 times 2. Then I sum all these products, and this is the element here. Then I take the second row, I multiply it by the first column, and this I multiply in this sense, and I get this element. And then I take the second row and the second column, and I take the element 2. Okay? Okay. This is, it seems complex, but it's not so complex. So, if you have a trick, if you have a matrix A m times n and a matrix B n times p, then the resulting matrix is m times p. This is a real look at this example. 2 by 3 multiplied by a matrix which is 3 by 2. The resulting is 2 by 2. Okay? The rule is m times n multiplied by n times p. This is the matrix A. This is it's the blackboard of Harry Potter. Why? Maybe I will not be able to come back anymore. But so I have m times n is the matrix A. Then I multiply it by a matrix which is n times p. These are the dimensions. So the multiplication is possible if these two elements are the same. And the result is a matrix which is m times p. Okay? This is the rule. It's similar to the fact that m simplifies in a way, but it's not true. So, just to remember. Okay? Okay. Okay. This is the row by column control. I don't want to. No, I want to let you a bit more confusing, since you, in principle, you can define another kind of multiplication, which is, as the summation, the multiplication element by element. So you take two matrices which are equal, and then you can define the element-wise multiplication. Okay? But in general, for the theory, the multiplication of matrices is this one. Okay? In Python, you have two operators, one for this multiplication and the other one for the element-wise multiplication, which sometimes is very useful for programming. Okay? So be extremely careful when you use the multiplication operators. Okay? There are two different symbols. One is this one, is this multiplication, and another one is the element-wise multiplication. I want to stress that for all these theoretical aspect, the multiplication is this one, is the row by column multiplication, and we'll see in a moment why. Okay? Okay, what are the properties of this operation? Well, the properties are quite easy. Well, no, not easy, but quite intuitive in general. But so they are distributive. They are distributive with respect to the sum, with respect to the product, in different way. But so all the property of the multiplication can be proven to be still valid. All but one, which is quite important. This kind of multiplication, well, say the mathematical term, is not commutative. Okay? So, you know the rule for products. When you change the order of the factors, the product does not change. This is true for numbers, but this is not true for matrices. Okay? We say that the multiplication is not commutative. You cannot change the order of multiplication. So A times B is different from B times A. This is very annoying in a lot of cases. So if the matrices are not, well, okay, to definition. If, so think about the matrix. A matrix is defined by the number of rows and the number of columns. Okay? So when the number of rows and columns are different, we can talk, we can say that the matrix is rectangular. Okay? when the number of rows is equal to the number of columns, we say that the matrix is a square matrix. So number of rows equal to the number of columns. Square matrix. Okay? So for a non-square matrix, so for a rectangular matrix, this cannot be true for dimension problem. So if you change the order, maybe the dimension does not allow for the multiplication. So the number of columns must be equal to the number of rows, and if you change the order, this is not true anymore. Okay? For square matrices, if you change the order, the dimension are okay for defining the multiplication, but it's not true that A times B is equal to the OB times A. So even for square matrices, the multiplication is not commutative. This is a very important problem. Okay? If I remember well, you will do some experiment, numerical experiment. Well, numerical experiment, it's too much, but you can try to do this calculation with Python and to see what happens if you use the multiplication operator in different way. Sometimes you get an error, if it's not possible. Otherwise, you get two different matrices. Okay? Okay. Why this kind of multiplication has been invented, in a sense, and became a very important tool in the matrix analysis, matrix theory, not theory, matrix notation, if you want. The reason is the following. For us, the reason is to not only see, but for us is the reason is the following. With matrices and operation with matrices, these kind of operations that I explained to you, so the matrix multiplication, we can express the linear system in a very compact form. Okay? So start from a system. This is a linear system in the original form. So this is called the canonical form of a linear system. Why is canonical? Be careful. We have the unknowns x1, x2, x3 on the left of the equal signs. Okay? Only on the left, not on the right. On the right, all is known. These are numbers, are considered known. Okay? On the right of the equality. So, the variables, the unknowns or variables, x1, x2, x3, are put in the same order in all the equations. Okay? So the first one is 1, the second is 2, the third is 3, and this is true for all the equations. Okay? This is a very during the exam in the bachelor degree, one of the typically in the exam of mathematics there is something, this kind of object. During the exam, one of the difficult questions is to during the exam is to change the order in the second equation, for example, and then in many cases I have to correct an error to the solution of the problem. So be careful that the system is written in this canonical form. Okay? Then, when it's written in this way, we can extract three matrices. Well, one matrix and two vectors. Okay? One matrix is the matrix of coefficient. This is the matrix A. Okay? You can read this matrix in different ways, but the first row are the coefficient which of the first equation. Okay? You see 3 minus 1 square root of 2. 3 minus 1 square root of 2. Okay? The second row is related to the second equation, the third row is related to the coefficient of the third equation. Okay? Or you can look at the columns. The columns are the coefficients which are related to the first unknown, the x1. You look at the x1 is the first unknown, so the coefficient of x1 are 3, 0.2, minus 1. And so the columns are the coefficient unknown for every unknown. Okay? Then we collect the known numbers in a vector, in a column vector B, so all that is at the right of the equality. Okay? And then we collect all the unknowns in a column vector. Okay? Then, by using the row by column multiplication, we can multiply the matrix A by the column vector X. Okay? So we do the multiplication of this row by the column vector. So the multiplication is 3 times x1 minus 1 times x2, x2 square root of 2 times x3. We sum. What we get? The first equation. This must be equal to the first element of B. Okay? You follow me? Okay. So we can express a system by using the matrix notation. Okay? This is useful from a theoretical point of view. You know that if I want to say, okay, given a linear system, and I can only write this object. So this means that I have a matrix and a column vector, the x of unknown, and a column vector of B. Okay? And this is a linear system, written in a very, the complete way. This is the compact way. You have this kind of object with reference. It's more complex. But another important thing is that when you solve, you see that in order to solve this kind of system, we'll see what does it mean to solve a system. Typically, for example in Python, there are some commands and the input of that command for solving systems like this one is a function will accept as input the matrix A and the vector B, and gives as an output the solution X, okay? Which are numbers if the solution exists. Okay? So this notation is quite important, since with this notation we say, okay, this is a linear system whose dimension is given by the dimension of the matrix A. Then, in order to solve it, I only have to know the matrix A and the vector B. Okay? Then there are some computational techniques we'll see that will help us in solving numerically this kind of system. You know, you remember some techniques for solving systems like, well, this is a 3x3, so you can do this by a pen and paper, for example. Do you remember you were able to do this? Rouchet-Cavelli is a theoretical result that helps us the structure of the solution, but not the precise solution. Rouchet-Cavelli, as we will see, will give us an answer like, okay, this system has a unique solution. This is true, we don't know. It depends on the matrix A. Okay, that's the Rouchet-Cavelli. But what is the solution? It's typically, well, there are many, I know at least 3 different techniques to solve pen and paper with 3 or 4 techniques to solving this kind of system. One is substitution, for example. This is the easiest one. So you take first equation, and then you say, okay, x1 is equal to 2 minus plus x2 minus square root of x3 divided by 3. So you solve for one variable. Then include this one, this variable x1, which is written in terms of x2, x3 in the second equation. So x1 disappears, and you have something which is in x2 and x3. Then you solve for x2, and you get something in x3. You put this in the third equation, and you have a linear equation in one variable. This is substitution. Otherwise, there are some other techniques, which I don't know if we will review which are based on, they are called Gaussian elimination. So you substitute one row, one equation with the sum of the other two, for example, and then you get this a similar system which has the same solution, but it's easier, and so you consider it easier. Okay, but it's more or less is an art. Okay, to solve the system. Okay, some, I don't know, well, I know that it's this mathematical lecture, it's a bit boring, especially with this kind of topic, but if you agree with me, I will not do a break, and so we can finish 10 minutes before the 8. Okay? Yeah? Okay. Okay. So some special matrices. Okay. There are some very special matrices which are useful and which will appear in many contexts. So. A very special class of matrices are the square matrices. They are very special. Same number of rows, same number of columns. Okay? We will, in general, we will see linear systems in which the number of rows, the number of rows are the number of equations, the number of columns are the number of unknowns. They can be different in general. So we'll see a general result for all the possible situations. The square matrices, so square system in which you have the same number of equations and the same number of rows, correspond to the case in which the coefficient matrix, the matrix of coefficients, is a square matrix. So the square matrices are a special subset of all the possible matrices. Okay? So square matrices are matrices with same number of rows, same number of columns. So 2 by 2, 3 by 3, 4 by 4, 5 by 5, and so on and so forth. Okay? Okay. We'll see why they are special for in many situations, in many applications. It's in a sense it will be natural to consider these square matrices. Okay? In statistics, it's well. Okay, I don't want to introduce any other ideas. But anyway, consider a square matrix. Then a special square matrix is this matrix is the matrix that I wrote here, that you see in the slide, which is made up by all zeros except on the main diagonal, the elements of the main diagonal, which are ones. Okay? So the elements here in the position 1, 1, 2, 2, 3, 3, 4, 4, and n are called, is called the main diagonal of the matrix. Okay? So the elements 1, 1, 2, 2, 3, 3, and n are the main diagonal, is the main diagonal of the matrix. A matrix in which the main diagonal is made up by ones and all the rest of the matrix is 0 is called the identity matrix. Okay? Identity. Why is called the identity matrix? Well, the reason is that if you multiply on the left or multiply on the right an n by n matrix, you don't change anything in that matrix. Okay? So A times I, the identity, is equal to A. I times A, so the identity times the matrix A is equal to A. So if you multiply a matrix A, multiply on the left or on the right multiplication or left multiplication, a given matrix n by n by the identity, you don't change anything. Okay? So it's the identity since this matrix on the set of all square matrices plays the same role of the number 1 for the real numbers. So if you take any real numbers, multiply it by 1, you get the real numbers. Okay? Multiplication by 1 does not change the number. Okay? You follow me? So 1 by pi is equal to pi. Okay? And this matrix is the same for square matrices, this identity matrix. Okay? So it's the identity matrix. Other special operations. Okay? All these matrices that I will introduce you have the Python command. So the identity matrix can be defined with a Python command. This operation is a very useful operation, which you can apply, you can obtain by using a Python command. Okay? Well, the operation is this kind of operation is the transpose operation. Okay? Transposing a matrix means to change, to switch the rows to columns. Okay, so it's a sort of clockwise rotation in a sense. So take the first row and consider this row as the first column. Then the second row is the second column. The third row is the last row becomes the last columns. Okay? This is called the transposition of a matrix. And the symbol is something like this. You may find this prime, A prime, which means A transpose. In formulas, it means that I exchange the index I with the index j. So the element I, A, ij becomes A, j, I. It's very simple to write. Okay. This is the original matrix. The transpose is the matrix in which the row becomes the columns. Okay? In formulas, you have one matrix is made up by element A, ij, the index ij. The transpose is with the exchanged index. So the element 3, 2 becomes the element 2, 3. The element 1, 4 becomes the element 4, 1. Okay? So you exchange the position. Okay? The row becomes the column. And vice versa. Okay? Quite useful. If the matrix is square matrix, the dimension does not change of the matrix. N by n is still n by n, and n by n. Okay? But the elements can change. Okay? Unless the matrix is so-called symmetric. So if a square matrix is invariant with respect to transposition, then the matrix is symmetric. Okay? Before doing this, the transposition obeys some rules. Some of the rules are quite intuitive, especially the first one. So the first one says what? Start from a matrix, transpose it. So exchange the rows with the columns. And then change again, transpose the transpose, you get to the original matrix. Okay? So transpose and transpose, you get to the original matrix. Then if you sum and then transpose is the same that transposing and then summing. Okay? The only thing that you have to remember, which is a bit tricky even to prove with pen and paper, is that the transposition and the product have this strange behavior. So if you compute the product of two matrices and then transpose is the same, this is an equality, to first compute the transpose and then doing the multiplication, but in the other order. Okay? The order is important in multiplication. So if you take A times B and then transpose, you get B transpose times A transpose. Okay? These are all the rules which justify the name algebra of matrices. Okay, algebra means I'm learning to do some operations, some formal operation with this object. So the main object of matrices, and then I want to study, I want to introduce some set of operations. Okay. Okay, so we have seen the identity matrices. Then another very special set of square matrices are called they are so-called the symmetric matrices. These are very important and special class of matrices, as we will see, since they are very important. I'll show you why in a moment. Well, we will see the symmetric matrices in some applications in the future. But anyway, a symmetric matrix is a matrix in which the matrix is equal to its transpose. Okay? So what does it mean? That the element in the position I and j, row I and column j, is the same of the element in the position j and in the row j and column I. Look at this matrix. So the elements on the diagonal are all different, maybe, or they are all equal. They are. This is the element in the position 1, 2. Okay? First row, second column. This element is equal to the element in the position 2, 1. Second row, first column. So you have the equality of these two elements. And this is symmetric matrix. Okay? So the element outside the diagonal are equal. What happens for matrices 3 by 3? Okay, look at this element. This is the element in the position 1, 2. Okay? 1 first row, 2 second column. This must be equal to the element 2, 1. Second row, first column. So this element is equal to this one. Element in the position 1, 3. This must be equal to the element in the position 3, 1, which is this one. So first row, third column, equal to the element third row, first column. Then, finally, element in the position 2, 3 must be equal to the element in the position 3, 2. So 2, second row, third column, equal to the element in the third row, second column. Okay? And this is, okay? So, the message is, the elements on the diagonal are elements. They can be whatever you want. The element outside the diagonal must be equal by reflection. Okay? So the element here must be equal to this one, the element here must be equal to this one, and so on and so forth. You may see the matrix 4 by 4, the diagonal is this way, then this element is equal to this one, this element is equal to this one, this element is equal to this one, so this is the element in the second row, third column, equal to the third row, second column, and so on and so forth. So you can, in a sense, look at the matrix you know a symmetric matrix only by knowing the elements in the upper part of the matrix, so up over the main diagonal or down the main diagonal, okay, or below the main diagonal. Okay, all the other elements are equal. Okay, you follow me? Okay. Why these are important? Well, we'll see at least two situations in which this kind of matrices appears naturally. One is multivariate calculus. You know, have you ever heard about Hessian matrices? The matrix of second derivatives? Maybe, but we'll see this. So it's a matrix in which you compute the element of the matrix are the second derivatives of a multivariate function. Then, since the derivative with respect to one variable and then with respect to the other is, you can exchange the order in most of the cases, then the matrix is a symmetric matrix. And this property is quite important. Another very important matrix, so if you don't know the multivariate calculus, I'm sad, but we'll see these points exactly in the second part of the course, well, in the future lectures. Another matrix that I think that you know are the covariance matrices. You know what is a covariance matrix? A bit of statistics. Mean and covariance, variance and covariance matrix. So the covariance matrix is naturally, by definition, a symmetric matrix. And many of the statistical techniques that we see, multivariate regression, principal component analysis, are based on the covariance matrix of a set of observations. And this matrix, which is the main object, maybe is one of the most important objects in statistics and in the application, the statistical methods, are the covariance matrix is a symmetric matrix. By construction. So the properties of a symmetric matrix are very, very important. Okay? Okay, some special cases. When one of the dimension is 1, we call this special they are matrices, they are array. From a computational point of view, they are, of course, array. They are matrices, but they have a special name, and we call them vectors. Okay, so in the matrix theory, we have to distinguish between row vectors and column vectors. Okay. The component of the elements in the vectors are called typically components of the vectors. The ith component is the element in position I. When we will see at some, especially for the theory, but even more for the coding part, it's important to work properly with the dimension of the matrix of this object, the matrices and vectors in particular. So some operations can be defined for row vectors, some other for column vectors, and so on and so forth. Okay? I want to stress, just to give you an example of matrix multiplication, just to give you an example. Let's see if this example is no. Okay. I don't want to. Okay, I need a whiteboard. Okay, just to understand what we are doing, and I can do a numerical example. Okay, so take a vector A, like 1, 2, 3. Okay. And the vector B equal to 0, minus 1, 1. Okay? These are two vectors. One is a column, is a row vector, and the other one is a column vector. Typically, a bit of notation. Have you, I don't know if you noticed it, but in the slides, the vector, the column or row vectors are written in bold character, okay? And the elements are the main character, okay? This is just another notation, nothing special. Another possibility is that we denote, this is another notation. We denote the vectors with the underlying bar, okay? Since I cannot write with bold, on the blackboard, I identify the vectors with the underlying bar. Okay? It's just a notation. Okay? Sometimes it's more a physical notation, well, no, not physical, sorry. A notation by physics. Okay? Sometimes the vectors are something like this one. Maybe you already saw this kind of notation. But this is the notation for a vector. Okay? But don't worry about it. So, we can define a matrix row by column multiplication. Okay? And this way. This is the multiplication, and so this is 1, 2, 3 times 0 minus 1, 1. So, I am multiplying a vector with 1 row times 3 columns times a vector, so a matrix, with 3 rows and 1 column. So what is the result? 1. What is the dimension of the result? 1. So it's a number. You see, this is 1 times 0, 0, minus 2 plus 3, 1. Okay? 1. Well, unfortunately, it's exactly 1. It's dimension 1, but then the number is 1. Well, it's random. I randomly chosen this time. Okay? Okay, this is multiplication times. But we can also define the multiplication B times A. Okay? So this is the multiplication of the vector 0, minus 1, 1, times 1, 2, 3. So this is the multiplication of 3 by 1 times 1 times 3. So what is the result in dimensionally? What is the dimension of this other sign multiplication? 3 by 3. So it's a matrix. Okay, so completely different. Completely different. So this kind of object is a matrix 3 by 3, in which the first element is 0, the second element is 0, the third element is 0, then I have minus 1, minus 2, minus 3, and then I have 1, 2, 3. Okay? Okay. So this is just to let you show which kind of result have when you multiply two vectors. So when you will code will program some matrix or vector multiplication, you must be really very careful about the position of the multiplication. So first A, then so the objects are the same. It is sufficient to exchange the order of the vectors to get completely different things, completely different, by using the same row by column multiplication. Okay. Okay. So. Okay, I don't want to enter this last sentence too much. Okay. Okay. There is, maybe you already know, but there is a relationship between vectors, matrices, but more vectors, and geometry. Okay, so one is algebra, the other is geometry, which are in principle two different areas of mathematics, but they are strictly related. Why? Essentially, a vector, like this one, in this case it's not important the dimension, okay? A vector can be identified with a geometrical entity, which is a point in a given dimensional, is a multidimensional space. Okay? Just to be a bit more clear. Suppose that you have a vector with two components. Okay? So n, the dimension is equal to 2. Okay? We can identify the vector with dimension 2 as the points in a plan, in a Cartesian plan. Okay? You know what is a Cartesian plan? The plan R by R. Okay? Okay, you can well, plot this plan. These are the typical plots that we do. So a vector corresponds to a point. Okay? And this correspondence is true even for more for spaces with a higher dimension. Okay? So typically you can represent a vector as a point in a given set, which is the set of real numbers, of n-dimensional real numbers. This can be useful sometimes, and maybe you saw this well, in other courses, maybe in the high school. No. No. Okay. In the previous version of the system, it was sufficient to click one button to have the whiteboard. In this case, well, where is the new one? Okay. No. Okay. Well, what I'm saying is quite easy. So suppose that you have this is the Cartesian representation of R2. This is a plan with two Cartesian axes, and okay. So what I'm saying is that if I take a point in this plan, you recognize that this is a plan, okay, geometrical plan, okay, with the system of coordinates. Take a point here, okay. This point, how can you identify this point in the plan? Well, but it's sufficient to take the component x1 of this point and the component in the y-axis. This is x2. Okay? So this is the coordinate of this point here. Okay? So I can identify this point P, okay, P, with two numbers, x1 and x2. This is a vector. This is the correspondence. So a vector can be represented as a point in the plan. A vector with three components is a point in a three-dimensional space. A vector with four components is a point in a four-dimensional space. which is difficult to imagine, since well, we live in a three-dimensional space, and so typically we can represent a vector in this way. This is the reason why they are called vectors. Okay? It's a line from 0 to that point. It's an arrow, more than a line. It's an arrow from the origin. This is the point with coordinate 0, 0. And the extreme of the arrow is the point which have coordinate x1 and x2. Okay? All the operations that we can do with vectors can be represented as operations with in a geometrical point, from a geometrical point of view. Okay? This is the correspondence between vectors and geometry. Okay? I will use a few of these correspondence, very few, and intuitive, not so formal, but only very intuitive pictures like this one, just to introduce you with some properties, especially for eigenvector, eigenvalues, this kind of object, and the intuitive, graphical intuition may be sometimes may be more okay, more clear than the formulas. Okay, so this is a summary of the operation that we can do with vectors, but they are, well, this is the example that I showed you before. So you can define some difference, multiplication by scalar, the product with the depends on the dimension of the two objects, but we have seen an example, and these are some examples of matrix multiplication, operation with the vectors. Okay, you see, this is exactly the example that I showed you before. So row by columns, so columns by row. This is square matrix times columns, and so on and so forth. So very very basic operations. All these kind of operations can be implemented in Python. You have to learn how to translate this kind of operation in a Python command. So you have the hat, the star, the plus, the minus, and or you can use the matrix multiplication function, but you'll see with the teaching assistant. Okay, a very important do you have questions up to now? I want to do a very short break without exiting from the classroom. Otherwise, it's okay. Okay, another important notion. I'm trying to give you this lecture to give you many definitions. So it's quite important. Well, many. I hope that many of these definitions that you already know many of these definitions. These are the typical, at least for the economic and financial courses in the bachelor in Italy. There is always a course with Mathematica Generale or Calculus, in which most of the cases these kind of things are introduced. But anyway, you have to, you see, maybe now it seems a bit messy and a lot of definitions. But if you think with some time, you will see that these are very easy definitions, and that I'm sure that you are already you already know this kind of operations and objects. Okay, an important idea, well, an important structure which can be, which is expressed here is the concept of linear combination of two vectors. This is quite important since, as we'll see, this linear combination, this idea of this definition of linear combinations is very useful in portfolio theory. Okay. Anyway, the mathematical definition of linear combination is that you fix two vectors. In this case, the vector A and B. You see that what I'm telling before, in the slides, the vectors are written in bold, bold notation. This is not random. It's bold for vectors, uppercase letters for matrices, and lowercase plain text letters for scalars. This is more or less this is the rule that we use here in these slides. Okay, these rules can be slightly different from text to text, but more or less always the same. Okay, so we have two vectors which are fixed. So suppose that we are given two vectors, then we can define another vector with the same dimension by simply taking the scalar product of the first and then summing the scalar product with another scalar of the second vector and then summing them. Okay, so you take a number alpha, a scalar, multiply the elements of the vector A by alpha, then take a number beta, multiply all the elements of the vector B by beta, and then you sum. And you obtain what is called a linear combination of the two vectors. Okay, linear since you are simply multiplying the elements of the two vectors by some scalar, some number. So you are doing a linear operation. Linear means you multiply a number by another number. This is a linear operation. Okay, so this idea, this structure can be generalized to a number m of any vectors that you want. So A, B, C, D, whatever you want. So a linear combination of more than one vector. So this is the general structure. So the result of this operation, this is called the linear combination, is a vector of the same dimension of v1, v2, vn. Okay, this is just an example of computation. Quite easy. Why this could be important? This kind of operation can be important. Well, they are important for notational purposes in most of the cases. But anyway, take this example. Take this example. This is the one of the possible notation for expressing this quantity. So take a portfolio with 3 assets. Okay, and suppose that I have four shares of the first asset, 2 shares of the second asset, and 1 share of the third asset. And okay, so think of this asset as the Tesla, Meta, and IBM. Okay, then someone says us that the price of the first asset is 100. So this price is the prices of each asset. These are expressed in euros, for example. So 100 euros, 80 euros, 120 euros. Okay, these are the market values. Okay. Then, what is the value of our portfolio? Well, it's quite easy. I have 4 shares of the first asset. The first asset worth 100 euros. So the first asset, the position of the first asset is 4 times 100, so 400. Okay? Right? I know that at this time, even very trivial things can be difficult at 7:30 almost, but anyway, it's quite, it's easy what I'm saying. So I have 4 assets, 4 share of the first asset, and then the value of each asset is 100, so the value of the position is 4 times 100. The value of the second position is A2 times B2. The value of third position is of the third asset is A3 by the price of the third asset. So essentially this one, A1 times B1 plus A2 times B2. So the sum of this product, but you can recognize that this is exactly the definition of a matrix multiplication. Okay? So we can express this quantity as the multiplication of the shares, of the number of shares of each asset in a row vector, okay, times the column vector of the prices. So this quantity can be expressed in terms of the operations of the matrix operations. Another kind of operation that we can introduce is to give a name to this object, which is the sum of the product of the elements. We will not explicitly use this kind of operation, but it's important that you know that they exist, since the reason is that there are some Python commands for doing this calculation, this kind of calculation. Okay? So this is called the inner product, but it's always the same. The operation that you do is always the same. The sum of the product. So you can call row by columns if the vectors are properly considered, or you can call inner product between these 2 vectors, so with the same dimension. It's a bit confusing, I know, but we are giving the different names to the same kind of calculations. I know that it's a bit confusing, but in Python and in MATLAB, in R, there are some special commands for doing this, for implementing this calculation, this kind of calculations. So you should know the name. The result is the same, but you can do this in different ways. Okay? And you will see some examples. Okay. For this lecture, I want to start to introduce this number that can be computed for each square matrix, which is a very important property of any square matrix. Okay? This is the last thing that we do now in this today. Okay? Okay, so this number, so the idea is that we would like to compute, to see what are the characteristics of a given matrix. And one very important number that can be computed for a given matrix is the so-called determinant. So the starting point is that this number can be computed, is defined only for square matrices. So we are looking at square matrices. Okay? So the input is a square matrix. Okay? I talk about input since I show you how is defined this determinant in such a way that you can compute it by pen and paper, in principle for every matrix, but you see that the definition is a bit tricky. Okay? But in general, we have a Python command to compute this quantity. So the input is a matrix, square matrix. The command is determinant or numpy determinant, and p numpy dot determinant that, and then the program, the function Python will compute the determinant by using completely different rules. Okay, but anyway, don't care about it. There are some computational techniques for the computation of this object, which are not the one that I'm using here. This can be used for calculation pen and papers. Okay, but I want to say immediately that the only matrices for which you can compute the determinant is at most 3 by 3, or matrices with a special structure that we'll see in a moment. Anyway, so there is a definition of determinant, but the theoretical definition is very difficult. Okay, really very difficult. I show you. This is a slide just for your knowledge. You can read the slides, but no one will ask you for remembering this definition. Okay? This is just so that you see that the real definition is someone very complex. It's based on the permutation of product of elements of the matrix, all the possible permutations. It's a combinatorial definition. But anyway, let us take a more operational definition of the determinant. Okay? Operational definitions means that essentially we can use this rule that I show you for in the two cases for an iterative procedure. And so in principle you can compute with this rule the determinant of every matrix, but as you will see in a moment, this is very the number of computation that the product that you have to do grows exponentially. Okay, with the dimension of the matrix. Okay, but anyway, so take this as the definitions. Okay. So these are the definitions of the determinant for a matrix of order 2 and a matrix of order 3. Okay? Take this one as the definitions, but the rationale behind this is it's well known, but it's a bit more complex. Anyway, start by a matrix 2 by 2. So the determinant is quite easy. It's the product of the element in the main diagonal minus the product of the element out of the diagonal. Okay? So A11 times A2 minus A21 times A1. This one. Okay? Maybe you already know this point. Okay? This calculation. So the product of the element of the main diagonal minus the product out of the diagonal. Of the element out of the diagonal. Okay? Take this one as the definition. Okay? No reasons, just the definition. The reason is the theoretical definition, but it's quite difficult. Okay? Okay? Same thing for the a matrix 3 by 3. So there are some tricks for the computation of this 3 by 3 matrix. There are at least, I know at least for this kind of matrices, 3 by 3, at least 2 ways to compute this determinant. Okay? Maybe the rule that you know is the following. I can't remember it, but anyway, take this matrix. called the Sarrus rule, okay? And I have to add the two columns here. Let us see the two columns of the first one of the second derivative. It is this one. Okay. Then I take all these diagonals, this one, and this one. I take the product of these diagonals, so A11, A22, A33, A12, A23, A31, A12, A23, A31, yes, sorry, that's okay. Okay? And then subtract the product of these three other diagonals. Okay? And you get this result. This is called the Sarrus rule. I want to stress that this rule for the computation of determinant is valid only for 3 by 3 matrices, no other matrices. Okay? 3 by 3. This is a quite simple way to remember for the computation, pen and paper, of the determinant of a 3 by 3 matrix. Okay? You add the first two columns and then you compute the first 3 to 1 to 2, 1, 3 to 1 to 2, okay, this one, and then subtract the anti-diagonals. 1, 3, 2, 3, 1. 3, 2, 3, 1. Okay, this one. This one and this one. The red one with the sign minus, well, the sign of the product. If one of the element is negative, the sign rule is still valid. Okay? So, minus without plus. Okay? Okay, so these are the rules for the computation of the determinant for a 2 by 2 matrix and for a 3 by 3 matrix. Okay? Then we could iteratively define the computation of the determinant for the 4 by 4 matrix, and then for given the 4 by 4, we can compute the 5 by 5 matrix determinant, and so on and so forth. Okay? This is one technique that we you only have to remember these two determinants. Then exercises pen and paper more with dimension more than this one are not just calculation, very boring calculations. This is the application. You can try to see if the two rules that I gave you, if you are able to compute this one. Luckily enough, of course, there is a Python command for the computation of the determinant of any order, of a square matrix of any order. There is a very powerful algorithm for the computation of the determinant. Oh, consider that for an applied point of view, we are doing an example of the computation of the determinant, which will enter in the solution of a linear system in the property of a matrix. The computation of determinant, as we'll see, is very important. We are looking at determinant of matrices 3 by 2, 3 by 3, but in applied problem you can have matrices of 1000 times 1000 elements. So you can imagine that the computation of determinant with this is a very difficult problem for computational functions. Okay? Okay, these are some examples. This is the definition. I want to stress one property. This is not, maybe it's written. Yes, it's the last one. I want to let you know this is important for many exercises. So take the note of this. If the matrix is a diagonal matrix, diagonal means that all the elements which are in the main diagonal are different from 0. The elements out of the main diagonal are equal to 0. This one. This is a diagonal matrix. Okay? What is a diagonal matrix? A matrix in which the elements outside the main diagonal are 0. Okay? Then, for this matrix, the determinant is easy. It's the product of the element in the diagonal. Okay? So you take the product of the element in the main diagonal and you get the determinant. Okay? So in this case, it's 1 by 2 by 1. So 2. Okay? So the diagonal matrix, this is a diagonal matrix, is very easy to compute the determinant. Another case in which it's very easy to compute the determinant, and this could be important in some exercises, is the case of a so-called triangular matrix. A matrix is triangular if the element below or up the main diagonal are 0. Okay, so look at this one. This is a matrix 3 by 3. The element below the main diagonal, okay, are 0. Okay? It's difficult? No. You have a square matrix, you have the diagonal, you can look at the element over the main diagonal and below the main diagonal. If all the elements over the main diagonal are 0, this is called lower triangular. If the elements below the main diagonal are 0, this is called the upper triangular matrix. Okay? So these are very special matrices, very special and very important in the application. Okay? For these matrices, the determinant is the product of the element of in the main diagonal. Quite easy, like the diagonal one. Okay, so nothing to compute. You don't apply the rule, the complex Sarros rule, the computation. Has nothing to do. It's simply the product of this one. 1 by 1 by 4. 4. This is an upper triangular, lower triangular. So the determinant is 1 by 1 by 1. 1. Nothing to compute. Okay, and this is valid even for matrices of dimension that you want. Not only 3 by 3, 2 by 2, but 4 by 4, 5 by 5, n by n. If you have a lower or an upper triangular, the determinant is the product of the main diagonal. Okay? This is quite important property. Then we have some rules for the determinants, saying that if you have, these are important for the computation, the element in one column or the element in one row of the matrix are 0, then the determinant is 0, nothing to compute. Okay? Then the transpose matrix has the same determinant of the original matrix, so if you transpose, the determinant does not change. If you multiply one row by a scalar, the determinant is multiplied by a scalar. Then if two rows or two columns are equal or proportional, the determinant is 0. This is, let's see, look at this one. This matrix has determinant 0, means that well, this may happen for several reasons. In this case, you see that the first row is double of the second row. Double means each element of the first row of the second row is multiplied by 2, and then we get the first row. Okay? So this means proportional. The second row is proportional to the first row. Okay? In this case, the determinant is 0. You see, even in this case. Okay? The first row is proportional to the second row. Determinant is 0. Okay? Another important property is that if you do the product of the determinant of the product is equal to the product of the vertices. This is very difficult to prove, but it's a nice property. This one is a consequence of the third one. And the last one is what I'm trying to say before. So if you have a triangular matrix, lower or upper triangular, the determinant is simply given by the product on the main diagonal. Okay? Okay, so these are the main properties, and we can stop here the lecture. The thing that you have to remember from this lecture, so what is a matrix? Okay? Operation between matrices, sum, subtraction, quite easy. Row by columns multiplication between between matrices. Okay? Row by column multiplication. So the matrix multiplication. Then identity matrix for square matrices. Transposition of matrices. Determinants. And the definition of identity matrix, diagonal matrix, lower and upper triangular matrix. Okay? These are the things that we will use okay? So, we'll see Wednesday, right?
Wednesday.
Okay, bye.